Today, we are diving into one of the most incredible frontiers in AI. We're talking about models that don't just understand text, but can actually see the world through images and video. It's AI that's learning to see and speak, and believe me, the implications are absolutely massive. So let's get right into it. I mean, just think about that for a second. What if an AI could look at a photo and not just process the pixels, but actually get it? Understand the context, the emotion, what's happening. That's the powerful idea we're going to unpack. And it's already changing everything about how we interact with technology. So here's our game plan. First, we'll nail down exactly what these models are. Then, we'll pop the hood and peek inside to see how they actually think. After that, we'll get into how they're trained, check out some mind-blowing real-world uses, and finally, we'll get real about the big challenges that are still ahead. All right, let's start at square one. Before we get lost in all the technical details, what exactly do we mean when we talk about a seeing and speaking AI? Okay, so the official term is a vision language model, or VLM for short. Think of it as an AI that bridges two completely different worlds. The world of sight, which is computer vision, and the world of words, which is natural language processing. The result is this amazing single system that can look at a picture and describe it, answer questions about it, even follow complex instructions based on what it sees. So, knowing what it is one thing, but the how does it actually pull this off? Well, to get that, we need to look under the hood at how these things are built. At its very core, a VLM is really a team effort. It's a collaboration between two different kinds of specialists, one that's an expert in language and one that's an expert in vision. Think of these two parts as specialist translators. You have the language encoder, often based on tech like GPT that takes words and turns them into a special mathematical code called an embedding. It's a way to capture not just the words, but their meaning and context. And right next to it, you've got the vision encoder, which does the exact same thing, but for images. It breaks down all the colors, shapes, and objects into its own mathematical code. The real magic, and the hardest part, is getting these two very different codes to speak the same language. So how does the vision part even work? It's actually a brilliant idea. A lot of modern VLMs use something called a vision transformer, or VIT. What it does is it takes an image and basically chops it up into a grid of little squares, or patches. And then, and this is the genius part, it treats that sequence of patches just like a language model treats a sequence of words in a sentence. It analyzes how all those little pieces relate to each other to build a deep understanding of the whole picture. Okay, so having these two powerful parts is great, but they're totally useless if they can't communicate, right? So how on earth do you teach an AI for words and an AI for pictures to speak the same language? Well, that's where the training process becomes the absolute secret sauce. Now, developers use a whole bag of tricks to get these models up to speed. There are several really advanced methods, but we're going to focus on two of the big ones that really form the foundation of how this all works: contrastive learning and masking. Contrastive learning is, at its heart, a giant game of memory match. The AI is shown millions and millions of pictures that have captions. Its job is to figure out which description goes with which picture. And it learns by basically pulling the math for a correct image-text pair closer together in its virtual brain, while at the same time pushing the math for incorrect pairs further apart. Over time, this creates a shared space where a picture of a cat and the words, "a fluffy cat," mean basically the same thing to the AI. And when I say a giant game, I mean it. The scale is just mind-boggling. For instance, the super influential CLIP model from OpenAI, it was trained on a dataset of 400 million image and caption pairs that were just scraped from across the internet. It's that sheer volume of data that allows the model to learn all the subtle connections between what we see and the words we use to describe it. The other key training method is called masking, and you could just think of it as a fill-in-the-blank game. Sometimes the AI gets a picture and a caption with a word blacked out, and it has to use the image to guess the missing word, like playing. Other times, it gets the full caption, but a piece of the image is blacked out, and it has to try and reconstruct what's missing. Both of these games force the model to build a way deeper, more contextual link between vision and language. So you go through all this incredibly complex training. What do you get at the end of it? Well, you get some seriously powerful capabilities. Let's take a look at how these models are actually being used out in the real world, right now. The list of things you can do with VLMs is already huge, and it's growing like crazy.
We're talking about everything from automatically writing captions for your family photos to generating brand new photorealistic images from just a text prompt. Let's dig into a few specific examples that really show off how versatile these things are.
You know that frustrating feeling when you're shopping online? You know exactly what you want to find, but you have no idea what keywords to type in. You just want to say, find me that blue jacket I saw last week with the silver zippers. Well, VLMs are making that a reality. They are completely changing how search works. And then you've got robotics, which is where things start to feel like they're straight out of science fiction. A robot with a VLM doesn't just see a soup of pixels anymore. It can actually identify objects, understand how they relate to each other, and follow a command like, hey, please pick up the red block. That is a massive leap forward for how machines can interact with the physical world. VQA, or visual question answering, takes it all a step further. Here, the AI isn't just seeing things, it's reasoning about them. So for example, a system could watch hours of road inspection footage, a super boring job for a human, and not only spot every single pothole, but also answer questions about how severe each one is, and then automatically generate a detailed report for the maintenance crews. It's a huge time saver. So this whole field is moving at lightning speed. All the major tech companies are rolling out their own increasingly powerful models. But this kind of rapid progress doesn't just bring new features. It also brings some pretty significant new challenges to light. I mean, it really is a Cambrian explosion of new models right now. You've got OpenAI's GPT-4o, which is this unified model that gets audio, vision, and text. Then there's Google's Gemini and Meta's Llama 3.2, which are also pushing the limits. And what's really cool is that many of these are becoming open source, which is just pouring fuel on the fire for researchers everywhere. But of course, with this incredible power comes a whole new set of problems. And when you merge these two really complex systems, vision and language, you get some unique challenges that researchers are now scrambling to figure out. And these are not small issues. First, there's bias. If you train a model on the internet, well, guess what? It's going to learn all of our human biases too, and sometimes even amplify them. Then there are hallucinations, which is a nice way of saying the model just makes stuff up and states it with 100% confidence. They also have a hard time with brand new concepts they've never seen before. And on top of all that, the sheer cost and complexity to build and run these models is, well, it's immense. So that leaves us with this final, really big thought. We are actively, right now, teaching machines how to see and interpret our world. As this tech gets woven deeper into our daily lives, the questions get pretty profound. What do we actually want to point this new vision at? And maybe even more important, as it gets smarter, what conclusions is it going to start drawing all on its own?